All right, so now we're going to move on to step 2, solving an equation of motion. So here we have some equation of motion, mx double dot plus kx equals 0. And remember that this could be some equivalent mass based on the geometry and the mechanics of the problem, and this could be some equivalent spring. But it's always in this form for undamped vibrations. So what we could also say here is that this is the type of problem for which the acceleration is going to equal negative kx over m. So the acceleration is proportional to the position with some proportionality constant that's going to be negative kx over m. So if we start with imagining our spring mass system like this, and we displace it, we pull this spring down a certain amount, and that amount is x0. Let me turn off this glare. All right, so we have this x0, and so we start out, if we look at the time, and we start out with this x0, this is our maximum, but it doesn't have any velocity, so it starts to accelerate, and it accelerates more and more, until it gets close to 0, where it's at the equilibrium position again, but it still has some velocity, and now there's no acceleration, so the velocity continues, and it goes past the equilibrium position down. So actually, this is, if we think about this as x, so we pulled it down, started here, it goes past the equilibrium position, and then up here again to some maximum position, which is here, and then, oh look, now at this maximum position, the acceleration is in the opposite direction, again, from the position, so that pushes it back towards the center again, and again, when it comes to the center, it has 0 velocity. So this is supposed to be sort of a curve. And then it comes again down to the position that we pulled it to originally, because in this particular problem, there's no damping, so there's no energy loss. The energy just goes between the kinetic energy of the mass and the spring potential energy of the spring, back and forth, and it will do this forever. Right, so it comes up with this nice oscillating behavior, and if we had started it instead of with some position, but if we had started it by giving it a kick of velocity, let's say we started at the 0 position, but we gave it some velocity in this direction, right, that would just be like starting at a different point on this plot, right? We could start it here, and then it would go up, and then it would come down, and then up and down. And similarly, we could start it out by pushing the spring up here to start out with some position with a negative x, and that would be like starting here, where it's going to oscillate and oscillate, right? And so by this point, I hope you're sort of recognizing the shape that we're drawing, and you may remember this from math. There's a very special series of family of equations for which this is true, and it is in fact sines and cosines for which this is true. So we're going to write, let's say x is going to be equal to a cosine omega t. Actually, I want there to be more room here, so I'm going to erase this again and say we're going to put give ourselves some more room. So we're going to say that we think, based on those properties, we're going to say x is equal to a cosine times some frequency plus b sine some frequency times t. And this is, we're going to guess this is the solution to this differential equation. And then when we take the derivative here, x dot, we're going to have a omega sine omega t, and then we're going to get a negative sign here, plus b omega cosine omega t. So when we take the derivative again, we're going to get negative a omega squared. Oh, yeah, now we need a cosine here. Cosine omega t minus b omega squared sine omega t. So we're just taking these derivatives. Oh, and look, this is just as we had hoped. we have x double dot equals negative omega squared times x. So in fact, it doesn't matter what a and b are, any solution in this form we will satisfy this equation. And now we also know, we can see that because from here, remember we had immediately written x double dot equals k over mx. So now we know that, oh, and there's a negative sign here. And now that we know that omega squared has got to be equal to k over m. So omega squared has got to be equal to, oh wait, omega has got to equal the square root of k over m. So it doesn't actually matter the initial conditions here. Whatever mass and spring that we have, no matter how we perturb that, whether we give it an initial velocity or initial displacement, no matter how much the initial displacement is, we know that we're going to have some frequency of the square root of k over m. And now the units of this frequency are going to be in radians per second, right? Because that's what we're going to input here. We're converting this time in seconds to this input to a cosine, which we want to be radians. So these units are going to be in radians per second. We'll just use 2 pi if we want to convert that to like periods or frequency in cycles per second. Okay, so the other thing to point out here is that for your particular problem, you might have different A and B. And A and B will control the phase and the amplitude of the sine wave that you're working with, right? So for the one I originally drew on the board here, where we have some t and some xo, oops. Right, so this looks like a cosine wave here. So in this particular example where you start with some original displacement xo, then a equals xo and b equals 0. Right, but you could start it with a different combination of a and b, and you're going to solve based on the initial conditions, based on whatever, so your problem will give you some initial conditions and you can solve for a and b. Some people also like to put the format of their solution here, not in terms of A and B, but they like to say that the solution format should be x equals some amplitude times, you could pick a sine wave if you want, or I don't know, I like cosine, but you could pick either one. I like cosine because the original amplitude is going to be your original displacement. But you could alternatively have a phase here, and then this phase would be, so now it would just be one cosine curve with a phase offset, and you could similarly solve for that. I find this a little bit more convenient, so that's what I recommend, but you could do either way. All right, and so now you know that you don't have to do all of this work. When you get some equation with mx double dot plus kx equals 0, your solution is going to be x as a function of time is going to be some amplitude times the cosine of k over mt plus the sine of that same k over m, square root of k over m times t. So the way to solve these problems is you get this equivalent mass. Whatever's multiplied by the x double dot is the equivalent mass. Whatever's multiplied by the x is the equivalent stiffness. And then you have some solution x of time is going to be equal to some some amplitude of some cosine wave with this frequency, and some amplitude of some sine wave with the same frequency. And then so you would be able to solve, right? So if you know that x of 0 equals x0, then when you put 0 in for the sine, this term goes away, and then this term goes to 1, so that equals a. And x dot of 0 equals, so this would be the speed at the beginning when you let go. If that was 0, then that would be b, because you could take this whole derivative again like we showed, and we would have, this would have a sine term which would go to 0 at 0, and this would have a cosine term which would be 1 at 0. B times but so then in order for this to be true, b has to equal 0. All right, so there can be several different forms of the way these problems go, and you can begin on the homework, see if you have questions. I can do another example.